Welcome to our lecture online, and now we're going to take a look at the Markov chain in a little bit different way. We're just going to continue working this problem. We're going to take our initial state matrix right here and our probability matrix and just simply calculate the next state, the next state, the next state, the next state. And if we then keep going like that, you see something very interesting happening. Notice that initially the states change quickly. Notice we go from 0.316 to 0.346 to 0.356 to 0.358, and all of a sudden you begin to see the changes become smaller and smaller and smaller. It looks like the state matrix begins to converge to a particular value or set of values. So this was a problem that we saw earlier in a previous video where we had three stores, let's say three grocery stores, where grocery store A received 200 customers, B 120 customers, and C 180 customers, and they had a probability matrix that showed how customers were expected to change from one store to the other, how many would stay loyal to one store and how many people would start shopping in other stores. And over time, using that probability matrix, we saw that the whole state matrix begins to converge to a stable state matrix right here. When we get to the 8th attempt right here, we notice we multiply the probability times the state number 7 results right here, which we placed over here. We multiplied that times the probability, and notice we got the exact same result as before. We saw that the state matrix began to converge. We can then say that the state matrix is now stable, or it's also called the stable distribution matrix, and we denote it by X with a line on top. That simply means it's now stable. Notice that store A now will have 228 customers, store B will have 177 customers, and store C will have 101 customers. So the distribution is now different. 46%, basically right here, of the customers go to A, 35% of the customers go to B, and 20% of the customers will go to C. And that's where it ends up. So the whole idea behind the Markov's chains is to look at an initial condition, a current state condition, then see the probability matrix, how things are expected to change, and then drive that through however many times it takes until the distributions matrix becomes stable. Once it becomes stable, we can then say that now this will be the new way in which things will operate until the probability matrix changes for some reason. Maybe there's something bad happened in store A, the prices went too high, they've had bad help, bad customer service, people are beginning to stream away from A, then our probability matrix will change again, and then we'll have a new distribution. This type of system is also used, for example, when we add new products to the market. Let's say a new toothpaste and want to break into the market. So you do a lot of commercials, you get the new toothpaste on the shelves in supermarkets and in drugstores, and people begin to buy it, so you have some initial state. Now, if it's a really good product, then people will continue to switch to that new brand. If it's a bad product, then people will not switch, and they may switch back, and you start losing customers. So based upon what people are doing, and you kind of poll people and you watch what they do, you can come up with a probability matrix and determine how much of the market you think you can handle, or how much of the market you think your new product will actually begin to take. And so we can predict those kind of things using Markov chains. So again, it's simple. You start with your initial condition right here, which is relative to the initial state that we had. So initial state times the probability matrix gives you the state one period later. The period could be a day, a week, a month, a year, whatever it is. And so you take those results in here, multiply times the probability matrix, so you get your next state. Let's say these were the grocery stores, and we look at it week by week. Notice how the state continues to change, but the changes begin to get smaller and smaller and smaller. Towards the end, they become very small, and in the very end, they become stable, meaning you now go and multiply this another 100 times, and you will not get any different results. You now have a stable distribution matrix, and that's the end state that we're looking for. And in future videos, we'll see all kinds of techniques, how we come up with the final state matrix. Especially, it may take 50 of these steps, and if it takes 50 steps, you definitely don't want to do this 50 times. You want to find a shortcut method to do this, and yes, indeed, there are shortcut methods, and we'll show you how to use those.